Well, pre-calculus classes, as always, good morning, good afternoon, or good evening. We are going to follow up what we did with section 3.1 now with 3.2 with logarithms and talking about their graphs as well. Those two sections really do go together well. So, one of the things we looked at in Chapter 1 was finding inverses. If we asked you to find the inverse of y equals b to the x, well, the first thing that you do, you switch your x and your y's, so x equals b to the y. And then if we try to get y by itself, there is nothing that we can mathematically do that will allow that. You can't divide b over. The exponent is connected to it. You can't do anything like trying to take a root, because the variable's a power, that won't work. The only option was creating a new mathematical expression. And that new mathematical, I guess not necessarily expression, but that new mathematical process is what is called a logarithm. So you can't solve for that exponent without a new form, which again is a logarithm. So if you have something like y equals b to the x, this is in exponential form. We can rewrite that exact same expression in log form by writing it as log, and then this is base b of y equals x. Y has to be positive, the base has to be positive, the base also can't equal 1. So if we come back up here to this, well, y equals b to the x, here we have x equals b to the y. So when I rewrite this, it's always log, and then the base is whatever your base is in the exponential expression. And then whatever is right here, what the expression equals is what goes inside your logarithm. So the log base b of x equals y. So the only way to get y by itself, again, we had to create that new mathematical form of a logarithm. So, as far as how these work, I'll admit one of the things I always like to do, turn it into an equation, log base 2 of 32 equals x, and then you set it up in exponential form. So 2 to the x equals 32. Now, things like this, we will certainly ask you to evaluate some simple exponential expressions without your calculator. And, it's just a matter of, okay, 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is 32. This next one, again, if you want, set it equal to x, so 4 to the x equals 2. And this one is where you can almost kind of think of it as, if we're going to go from 4 to 2. Well, 4 to the first is already 1, so it is going to be a fraction. The fractional power that we're going to need, and I'm even going to talk about this in another way in a moment, is 1/2. And basically what a 1/2 power is the same thing as is a square root. The square root of 4 is 2, so 4 to the 1/2 is 2. Log base 10 of 1 over 100, well, 10 to the x equals 1 over 100. I know when we were graphing the logarithm, or not the logarithms, the exponential functions the other day, this issue showed up there. If you have a base and you end up with a fractional answer, you're going to have to involve a negative exponent. Well, ignore the fraction initially. What power of 10 is 100? Well, 10 to the second is 100. To make it a fraction, we need a negative exponent. So it's -2. The next one, log base 3 of 1 So 3 to the x equals 1. Well, if I need an exponent to make something 1, it's 0. Log base 5 of 5. So 5 to the x equals 5. Probably the easiest one yet. X is 1. Now this last one, 8 to the x equals 32. Well, 8 to the first is 8. 8 to the second is 64. So it's somewhere between 1 and 2. Now, unlike this one where, the square root of 4 is 2. Square roots aren't going to help us here. This is the one instance where what you can often do is find a base that each of these can be rewritten as. Well, we can rewrite 8 as a power of 2. It is 2 to the third. And then 32, well, we just found that's 2 to the fifth. So basically, when you have the same bases here, all that we need to do is set the powers. So 3 times x, 3x equals 5. So this one is 5/3. So again, we said it's somewhere between 1 and 2. That, that leaves a lot of numbers out there. That specific fraction, 5/3. So, properties of logarithms. Well, as we work through this chapter, if you have log base b, any base of 1, it's 0. If you have the log base b of that same value, log base 5 of 5, it's 1. Now, if you have a logarithm base and this value in there to a power, well, it's kind of like what we just had here, log base 5 of 5. Well, if you have this power, whatever power, as long as the base and this value are the same, whatever the exponent is will be your answer. So that one is just x. Now, kind of the same thing. Logarithms and exponents are inverses of each other. So that's why you have a logarithm and an exponent, it's x. Here we have a logarithm within an exponent. Again, because these are inverses, it is also equal to x. If you have log base b of x equal to log base b of y, as long as the bases are the same, x and y are equal. It's kind of like what we actually just did up here, except instead of with logarithms, exponents. Properties of natural logs. Well, the base is e. That is one thing that, sometimes, if you want to even think of it as log base e is the same thing as natural log. So, if you have the natural log of 1, it's also 0. If you have the natural log of e, because the base is e, just like up here, it's 1. Again, natural log, because the base is e, and this is e, back to just the exponent. And then this one, much like up here, again, because our base is e, you're taking it to as a power of e. They're inverses, and all you're left with is x. And then here, if you have natural log of x equals natural log of y, then x equals y. So these are all kind of the same. It's just a matter of general logarithms, natural logarithms, where our base is specifically e. All right, so doing some solving here. Again, as we said, log base 4 of x equals log base 4 of 5. Well, bases are the same. X equals 5. Now, obviously, we'll get more complicated than that. Log base 7 of 7 equals x. Well, here you're going to take the base 7 to the x equals 7. And then x is 1. All right, this next one, again, If you want to set it equal to e, also remembering that our base here is e. So if we set it up as an exponent, e to the x equals 1 over e. Well, again, we are turning something into a fraction. That means we need a negative exponent. So that negative exponent will be -1. All right, coming back to our properties, if you have e to the natural log of 5, again, because our base here and our logarithm base are the same, whatever is inside the logarithm is your answer. So this one is just 5. All right, for this next one, natural log of 1 over 3, well, then any logarithm of 1, be it a regular base or the natural base e, is 0. 0 over 3 is 0. And one final one here, the natural log of e. Well, again, our base and the value inside are the same. Natural log of e is 1, so this is just 2 times 1, which is 2. So there are some problems where we are solving some very simple logarithmic expressions. Graph f of x equals 3 to the x, g of x equals log base 3 of x. Now, this goes back to something that we looked at in 3.1. This will be in section 3.2. So, if I set up for 3 to the x, well, 3 squared is 9. 3 to the first is 3. 3 to the 0 is 1. And then 3 to the -1 is 1/3. 3 to the -2, 1/9. So, when I graph the exponential all right, so there's our exponential. Now, graphing a logarithm, y equals log base 3 of x. Well, this is not going to be real easy to graph in its current form. What we're going to do, we're going to rewrite this in exponential form. Our base is 3 to the y equals x. Well, what's actually happened when this was y equals 3 to the x, now we have 3 to the y equals x. Our x and y have switched. If we're going to graph this now, because y is the exponent, we'll plug in for y. 3 to the second is still 9. 3 to the first is 3. 3 to the 0 is 1. 1/3 and 1/9. If you notice, our x and y's switched. That's because these are inverses. So 9, 2, 3, 1, 1, 0, and then that. All right, so these are reflections over the line. Y equals x. If you want to, you can even sketch that in, and you can even see that. Inverses are reflections over the line y equals x. For f of x equals log base b of x, your domain. Biggest change here is our domain. All the values are positive. So it's 0 to infinity. The range can be negative, positive, or 0. The x-intercept is 1, 0, which, if we look back at 3.1, you'll notice all of these switched. The graph now passes through the x-axis. The vertical asymptote for the logarithm is x equals 0. If the base of the logarithm is more than 1, it is going to be an increasing function. If the base happens to be between 0 and 1, the graph will be a decreasing function. And a couple of things here. You know, when you have something like this, again, the logarithm can be viewed as kind of a parent function as well. So if you have something like log base 3 of x minus 1 minus 4, well, we can do some transformations with this. The minus 1 inside the logarithm will shift it right 1. The minus 4 outside would move it down 4. So you could simply take, you know, all of these points, right 1, down 4, right 1, down 4, and so on. All right, this next one, you kind of have to be careful. And one of the reasons why they actually put this out in front is, you know, if we had this at the end as a plus 2, you know, you do have to kind of be careful. So this will shift it up 2. The negative in front of the logarithm, so this will reflect it over the x-axis, then up 2. All right, so there are, you know, how some transformations work. Find the domain of each function. Well, as far as what happens here, the natural log of x minus 2, this is going to shift it right 2. Well, the domain is 0 to infinity. If we shift everything right 2, that would put a vertical asymptote at 2. So this will be 2 to infinity. And I'll actually even specify that's our domain. Now the next one, the natural log of 2 minus x. You might want to flip this around, negative x plus 2. The plus 2 that's inside there, left 2. The negative x that is inside the expression will reflect over the y-axis. Now, you know, if you remember going back to transformations I talked about, first thing I always do, horizontal shift. Then any reflections, last thing, up or down. So, if we shift this left 2 and reflect it over the y-axis. Well, what's going to end up happening? Our graph is going to point left and have a upper limit for the domain. It is still going to be positive 2, but because it's reflected, go to negative infinity. And again, because of that vertical asymptote, parentheses on each of those. All right, one last one. The natural log of x squared. Well, when you have this value inside of your logarithm, well, when you have a number inside here, this can actually be moved out to the front. And so if you have 2 natural log of x, we'll actually talk more about this as we get into properties in the next section. But if you have a number out in front, all that's going to do is stretch it vertically. So if we stretch it vertically, it won't impact your domain. So it still is 0 to infinity. And again, as I said, when we get into 3.3, we'll talk more about why you can do that. You may even remember this from last year in Algebra 2 as well. But that finishes up everything in 3.2.